Assalamualaikum everyone, a very good day to our lecturer and fellow friends. Before we start, let me introduce our team. First, we are group 5 from class CEEC22265. I am Muhammad Arif, and joining me today are my group members.
Hi, my name is Izzati Binti Abdul Halim.
Hi, my name is Aida Sharina Binti Muhammad Fuad.
Hi, my name is Husnul Aqeelah Binti Rosfandi.
Hi, my name is Aina Alia Binti Muhammad Nazori.
And today, we will be presenting our project titled Sustainability, Water Supply and Wastewater Management for an Orang Asli Community. This project serves as a comprehensive engineering solution directed towards achieving SDG 6 and as well as SDG 14. To kick off our presentation, I would like to direct your attention to the first section of our poster. Our project focuses on a remote Orang Kampung Orang Asli community right here in Malaysia. As you can see from demographic background, the settlement consists of 100 households, making up a total population of 500 people. The fundamental issue this community faces is their complete reliance on untreated river water for their daily survival. Currently, they have absolutely no access to centralized water treatment plant (WTP). If you look at the key challenges diagram below, first we have untreated river water. Because they draw directly from the river, they are highly exposed to water contamination from physical, chemical, and biological pollutants. Second, limited electricity. The remote nature of the village means power is scarce, making it incredibly difficult to implement a standard conventional treatment system that requires continuous energy. Third, no wastewater system. Without proper infrastructure, 80% of their daily water usage turn into untreated wastewater that flow directly back into the environment, causing several river pollution. Finally, poor sanitization. All of these factors combined leads to a poor overall sanitization, which creates a massive health risk for the community, including exposure to waterborne disease and pathogens like E. coli. Understanding these four key challenges establish the key baseline for why we need an immediate sustainability engineering solution. Next is objective. To solve the issue we just highlighted, our study was driven by these three main objectives. The first one is water demand and wastewater estimation. Our first step was to determine the future water demand and the expected wastewater generation rate for the community. This estimation is critical to ensure our proposed system are sized correctly for their long-term needs. Number two, sustainability water treatment design. Our second objective was to propose a reliable and energy-efficient water treatment plan. It was essential that this design be specifically suitable for rural application, meaning it can operate effectively despite the community limited electricity. Number three, sustainability wastewater treatment design. Finally, our third objective was to develop a decentralized, nature-based wastewater treatment system. By utilizing low-energy treatment technologies, we aim to safely manage the community wastewater without relying on complex power-heavy machinery. Next is problem statement.
To present about the problem statement for this project, our group selected Kampung Orang Asli at Kuala Tembeling, Lipis, Pahang as our case study because it closely represents the assignment scenario provided. The village consists of approximately 100 households with a population of 500 people living in a remote forest area. The community depends entirely on untreated river water, has limited electricity supply, and does not have a centralized water treatment plant or wastewater treatment plant. Which is this condition made conventional high energy treatment system impractical, requiring a more sustainable engineering solution. Based on our investigation, the main issues start with untreated river water. As shown in the figure, the contaminants are classified into three categories. Firstly, physical contaminants, which include total transmitted solid, TSS, and also turbidity. This reduce water clarity and also indicate high sediment levels, especially during rainfall due to the surface runoff. Secondly, chemical contaminants, including biochemical sediment, chemical sediment, and also ammoniacal nitrogen. This parameter indicates organic pollution and oxygen depletion, suggesting that the river receives untreated domestic waste and also decomposing organic matter. Next, finally, biological contaminants, particularly E. coli and also other pathogens, which indicate fecal contamination and also significantly increase the risk of waterborne disease. These parameters are widely recognized indicator of river pollution and also are commonly used in water quality assessment. From an engineering perspective, these findings are critical because every contaminant requires a different treated mechanism. Physical polluter requires sedimentation and also filtration. Chemical polluter require appropriate treatment to reduce organic loading, while biological contaminant require effective disinfection. Therefore, understanding the characteristic of the raw water is essential before selecting any treatment process. As shown at the bottom of the figure, these contaminants lead into three major impacts, which is waterborne disease, river pollution, and also environmental degradation. Most importantly, poor sanitation causes untreated wastewater to flow back into the same river course used by the community, creating a continuous cycle of contamination and also increasing public health risk. Therefore, our investigation demonstrates that the engineering challenge is not simply to provide a clean water, but also to develop a treatment system that is technically effective, energy efficient, and also practical for a remote community with limited infrastructure. These findings form the engineering basis for our proposed water treatment plan and decentralized wastewater treatment system. Ensuring long-term sustainability while supporting to SDG 14 and also SDG 6. Thank you. Next.
Regulatory. So there's four standards that we use in our design. So the first one is DOE, Department of Environment Malaysia. The purpose is wastewater discharge and environmental protection. The second one is WHO, World Health Organization. The purpose is safe drinking water quality. And the third one is MS 1228, which is Code of Practice for Design and Installation of Public Water Supply systems. The purpose is planning and design. The last one is PAN, which is Suruhanjaya Perkhidmatan Air Negara. The purpose is regulate water supply and sewerage service. Next, we go for the literature review. There are 4 studies that we use as a guide for our study. So the first one, the key findings that we have been found is TSS, BOD, COD, NH minus 3N, and E. coli. It relevance by support water quality assessment. The second one is river pollution affects water quality. It relevance by support pollutant analysis. And the third one is water quality monitoring is essential, which is it supports water quality monitoring discussion. And the last one is filtration improve quality. That relevance by our study with treatment selection. Next, we continue with water demand analysis.
Next, I will be explaining the water demand analysis for the proposed water supply system. So the estimated population of Kampung Orang Asli is 500 people, and based on the Malaysian water demand guideline, the domestic water consumption is 180 litre per person per day. This given an average daily water demand of 90 cubic meter per day to account for a period of higher water usage. A peak factor of 3.67 is applied, resulting in a peak daily demand of 330.3 cubic meter per day. The projected future population is 782 people, and based on this projection, the design water demand is calculated as 140.76 meter cube per day. Approximately 80% of the supply water become wastewater, giving an estimated wastewater generation is 112.6 cubic meter per day. Finally, the required design flow rate of the treatment system is 5.69 liter per second, which is used to size the treatment units. Next is the design calculations.
Okay, I will present the proposed water treatment and wastewater treatment design. For proposed rectangular sedimentation tank, a rectangular sedimentation tank was designed to remove suspended particles and flux from the water through the gravity settling process. Based on the calculation, the proposed tank dimension is 7.02 meters in length, 2.34 meters in width, and 3 meters in depth. Next, the water treatment process or WTP. Okay. The proposed treatment process starts with river intake, screening, coagulation, flocculation, sedimentation, filtration, chlorination, and finally storage tank. This process helps to remove contaminants and provide safe water supply for the Orang Asli community. For comparison of sedimentation tank design criteria for WTP, the sedimentation tank design was compared with recommended criteria such as surface overflow rate, detention time, tank depth, and length to width ratio. From the comparison, all parameters satisfy the recommended design criteria. Moving to wastewater treatment process or WWTP, the proposed wastewater treatment system consists of collection system, septic tank, constructed wetland, disinfection, and river discharge. The septic tank provides primary treatment, while the constructed wetland further improves wastewater quality before discharge. Lastly, septic tank design criteria comparison for WWTP. The septic tank design was compared with the span requirement. The proposed septic tank achieves a hydraulic retention time of 24 hours, which satisfies the required standard. Therefore, the proposed WTP and WWTP system are considered suitable for the Orang Asli community, as they provide effective treatment, require low maintenance, and support sustainable water management. That's all for me. Thank you.
Next, we will continue with sustainability evaluation. So the first one is environmental sustainability. So our system improves environmental sustainability by reducing water losses, controlling sludge effectively, and using less energy. The next one is social sustainability. So the system provides safe water and proper sanitation, reducing dependence on untreated river water, and lowering disease risk. It also easy to operate and maintain by trained local operators. The third one is economic sustainability. So the proposed system is cost effective because it has a low operation and maintenance cost. It's simple and energy efficient design, make it affordable for our rural communities. The fourth one is SDG6 and SDG14 alignment. So our WTP and SDP support SDG6 by providing clean water and proper wastewater treatment. They also support SDG14 by protecting river ecosystem through compliance with Malaysian standards. Then we go for the EIA, Environmental Impact Assessment. So construction impacts can be minimized through the proper site management during operation, regular monitoring of pH, BOD, COD, TSS, and NH3-N, ensure compliance with regulation, and protect the receiving river. Next, we will go to the last point, which is practical feasibility.
So for the practical feasibility, this slide will present the purpose of water treatment system, which is evaluated based on the 4 aspects. The first one is the technical aspect, which the system follow the standard engineering practice, provide efficient treatment performance, and ensures a reliable water supply. From the economic perspective, it requires a relatively low initial investment. The use of gravity flow reduces pumping requirements, leading to low operation and maintenance costs. For the environmental aspect, the system minimizes pollution, improve water quality, and support sustainable development goals, which is SDG6 and SDG14, which focus on clean water and aquatic ecosystems. Finally, in terms of suitability, the proposed system is well suited for rural communities because it is easy to maintain, reliable, and can continue operating even in areas with limited electricity supply. Overall, the proposed design is technically feasible, economically affordable, environmentally sustainable, and suitable for Kampung Orang Asli.
I will summarize our main findings and how we achieve our objective. To our analysis, we determined that for our project future population of 782 people, the community will require a design water demand of 140.76 cubic meters per day. Correspondingly, they will generate 112.6 cubic meters per day of water that needs to be managed. To meet this sustainability, we have proposed a conventional water treatment plant alongside a decentralized wastewater treatment plant system. This wastewater system utilizes a septic tank for primary treatment, constructed wetland for biological treatment, and a final disinfection unit. We selected these specific methods because they are low cost, low energy solution tailored perfectly for this purpose setting. Ultimately, by implementing this integrated system, we can ensure a significant improvement in public health while successfully reducing river pollution in the area. We also have a few recommendations to ensure the long-term success of this proposed system. First, community empowerment is crucial. The residents of Kampung Orang Asli should be actively trained to operate and maintain the system. This builds local capacity and ensure routine upkeep without having to wait for outside help. Second, we must practice responsible construction. Environmental impacts during the building phase must be minimized through proper site management. This includes a strict erosion and sediment control, dust and noise management, and protecting the surrounding vegetation. Finally, proper maintenance protocol must be established. Regular sludge collection and treatment must be scheduled and carried out to prevent any secondary pollution from the septic tank. As civil engineering students, designing this system have reinforced the importance of balancing technical feasibility with real-world social and environmental needs. And that's all from us today from Group 5. Thank you so much for your time and attention today. Thank you.